So this is lecture number 4. We will continue our discussion on sampling switches. So if you recall, in last class, we were looking at sampling switches, right? Like, so this is our sample and hold circuit that we are right now looking at, right? And right now we are more interested in basically looking at how this particular switch is going to be implemented, because this has to, an ideal switch is very nice to think about in terms of mathematical analysis. It is also quite nice to think about when you are, trying to do it at a more system level thing, but then finally this has to be implemented. Right? So the implementation part of it, we said this can either be an NMOS switch or a PMOS switch, or it can be a CMOS switch, right? Basically, this is nothing but a transmission gate. Now, this is a much better option, we felt, because the variation of the on resistance with respect to the input voltage was the lowest among all the three, right? But still this also has, so if you plot R on versus V in, for CMOS it is probably something like this, right? But still it is going to have a certain variation with respect to input voltage. Now, why are we really bothered about the on resistance, the behavior of the on resistance? Towards the end of last class, I had mentioned that any parameter which varies as a function of the input amplitude is going to end up as being nonlinear. So today we will see why that is the case. Okay. So now this switch, as I mentioned in last class, can be implemented or can be denoted as something like, okay. So let's say this is V in, and this is the on resistance of the switch, and this is the ideal switch. Okay. So you have an ideal switch, and the actual switch is modeled like this. Okay. This is the actual switch. Now this on resistance is something which is a function of the input voltage. Now let us define the node voltage here as Vx. Okay. Now what is Vx? Vx can be written as V in minus the current that is flowing through this particular part, right? Current into the on resistance. Correct. Now let's say if Vn is some A cos omega t, okay, and let's say it is much smaller, omega is much smaller than 1 by R on into, let's call this as Ch, okay. So which means that the capacitor is pretty much tracking the input voltage in real time, right? And let's also assume that, let's also say that now we are considering when the switch is on. Okay, let me just put less than 1 by R on Ch. Okay, it is not necessarily extremely small. Okay, now what is the current that is going to flow through the switch? So one approximation that we can say is, because the output is fairly tracking the input well, right? Vin is approximately equal to V out, and therefore I is nothing but C dV out by dt, correct? Which can be approximated as C dV in by dt, right? Which is equal to what? C into A times omega into A times omega into cos omega t, correct? So this is the current that is flowing. Now what is the voltage Vx then? So Vx is nothing but Vin, which is A cos omega t, minus C times A times omega times cos omega t into R on, which is a function of Vn. Or in other words, let me just write that R on is a function of Vn, basically, correct? Or you can basically say it is Vn minus Ca omega times or C omega times Vn into R on, which is a function of Vn. Now, when we say that this R on has a dependence on Vn, right? We can kind of write any curve, right, as a function, as a basically you can express it as a polynomial, right? So R on, which is a function of Vn, can be written as R on time R on naught, okay, plus let's say some alpha 1 times Vn plus some alpha 2 times Vn squared plus some alpha 3 times Vn cube and so on. Okay, so this is a general way of describing any function, right? You have R on as being a function of Vn. So any curve can be expressed as a polynomial, right? And this is the polynomial. Okay, so now what happens? Vn minus C times omega times Vn into R on naught, which is a DC, which is a fixed component, plus alpha 1 times Vn plus alpha 2 times Vn squared and so on, correct? Now, if you look at this expression for x, what will you get? You will have some terms with R on naught, right, plus some terms with Vn, right, plus some, okay, sorry, actually you will not have any DC term, right? You will only have Vn times some terms plus Vn squared times, because the moment this term alpha 1 C omega multiplies, you will have some Vn squared terms and you will have Vn cube terms and so on, right? So if your Vn is a cos omega t, now here you will have cos squared omega t, here you will have cos cube omega t, right? And if you expand this cos squared omega t, you will have cos 2 omega t and some DC component. Here you will have cos 3 omega t and cos omega t, both the components, right? These are all trigonometric identities, all of us are familiar with. So what we are seeing here is that the voltage Vx, which is basically the voltage which is actually getting sampled onto the capacitor, right? This Vx, this is an ideal switch, right? So the voltage that is actually sampled onto the capacitor is no longer a scaled function of Vn, right? It also has 2 omega terms, 3 omega terms and so on. Okay. So what does it mean? So if you look at it graphically, let's say you give a 1 kilohertz tone at the input and you analyze what you get at the output. Basically, you'll have 1 kilohertz, you'll also have 2 kilohertz, you'll also have 3 kilohertz and so on. Okay. So the magnitude of these are all what are called as the harmonic distortion terms. Okay. This phenomenon is what is called as harmonic distortion. Why is it harmonic distortion? It is at the integral multiple of your input signal, right? So if you give 1 kilohertz, you'll get 2, 3, 4. If you get 5 kilohertz, you'll get 5 kilohertz, 10 kilohertz, 15, 20, and so on. Okay, you will not get other terms. If you give a input sinusoid, you will get a output sinusoid of the same frequency, and it's harmonic. Okay. Now this is what is called as harmonic distortion. Sometimes it is also called as HD, HD2, HD3, and so on. So HD2 is basically defined as nothing but the voltage, the amplitude of the 2 omega term divided by the amplitude of the fundamental term. Okay. Same HD3 is defined as the amplitude of the 3 omega term divided by the amplitude of the fundamental term. So you can go on and define HD4, HD5 and so on. Okay. Usually, depending on the degree of non-linearity of any system, you will go and define as many terms as are relevant. Otherwise, after that, it will just go below the noise floor. Okay. Is it clear? Is it making sense?
Yes.
Yeah. Okay.
Yes, sir.
Right. So now what are we saying? We are saying that if our switch is going to have a voltage dependent profile, right, it is going to cause problems. Right. That is the voltage that is going to be sampled onto the waveform. So another way to kind of understand it is, even this is kind of at the mathematical level. I'll just give you another maybe a graphical way to, or a more intuitive way to even understand this problem. Okay, let us I mean, for example, we'll just take an NMOS switch. Okay, just an NMOS switch. Now if you have an input signal which is like this, let's say, okay, this is your input. All right, now what will happen when the input increases, right? How will Vx be or Vout be? Basically, as the input increases, your Rout is, the Ron is high in this region. Right? So if you're kind of close to that 1 by RC point, you're going to see a big lag, right? There's going to be lag. And then what will happen? As your input goes low, here the Ron is very less, like the on resistance is very less, and now it is going to nicely track here. So now look at this other curve that I drew. It is really not looking like a sine wave, right? So it is going to have a slower slope here, right? And then it's going to be very fast here. Right? So this is more like, you know, to kind of graphically look at it. Now, even if you the frequency much lower, you will still see some of these effects coming in. Okay, all right. So this is the discussion on non-linearity. Let us also see what happens to noise. Okay, noise due to sample and hold circuit. Okay, so right now we are only looking at the switch and the capacitor. Okay, now in one of the previous classes we looked at the need to put a buffer at the input and buffer at the output. So definitely both those buffers will have noise. They will have their total input referred noise, which will definitely come into the picture. Okay, right now we are looking at only this sampling switch and what happens to the noise of this switch. Okay, so now we know that the switch is not ideal, it is having an on resistance. So we can denote this as we just now saw, it has a resistance, right? Now this resistance will definitely have some noise component, correct? So now this is our actual switch. So this is your ideal switch. This is the on resistance, okay, and this is the noise component. So what is the noise component? What will be the noise power spectral density for this thing?
4 kTr.
4 kT Ron, right? This is 4 kT Ron. 4 kT Ron is the voltage noise spectral density. Okay. So now, if you want to calculate the amount of noise that this resistance with this capacitance is going to give, what do you need to do? You basically need to have, we will basically find what is Vn. So this is V out. So what we are interested is Vn out squared. Right? So when we assume that the switch is closed, okay, we can evaluate it only, you know, when the switch is closed. Otherwise, you know, the noise doesn't flow, right? So what happens? You have 4 kT Ron multiplied by the transfer function of this RC filter, correct? It basically becomes the this h of f is nothing but the transfer function of this RC filter. What is this h of f? H of f can be written as what? This is 1 by j omega c divided by r on plus 1 by j omega c, or rather you can basically just you can write this as what, 1 by j omega r on c plus 1. Right? So what is the magnitude of h of f?
1 by root of omega
1
square
plus,
r square square.
yeah, omega, yeah, this is the expression. So now if you put this here, okay, you basically the total integrated noise, right? What is the total integrated noise? Till now we are talking about noise spectral density, right? That is for a 1 Hertz bandwidth, what is the noise that you will get at each frequency point. Now what is total integrated noise? It is nothing but integrating this Vn out squared, which is anyway a function of frequency, right, from 0 to infinity. So if you integrate this, what you will get? You will basically get 0 to infinity 4 kT r on divided by 1 plus, oops, where did it go? Yeah, 1 plus 2 pi f r on ch whole squared into df. Okay. So integrating this is easy. You can try it on your own. It kind of, you can substitute and make it in the form of 1 by 1 plus x squared dx. Okay. So this will be nothing but tan inverse of x, right? You had some network issue. Okay. Now can you guys see the screen?
Yes, sir.
Okay. All right. So if you integrate the form 1 by 1 plus x squared dx, you will get tan inverse. You can substitute the limits. Basically what you will see is, you can try to do this and then see. The final result is kT by c. Alright, so I would encourage you all to work out this simple integration. Okay. Now, if you look at this total integrated noise, okay, just to give you a little clearer picture, okay, it is like, the thermal noise per spectral density was like this. This is 4 kT r on. Okay. Maybe I should have just drawn a little higher. Let's say this is how it is, 4 kT r on. This is the thermal noise, which is flat across frequency. Okay, this is a per spectral density. The filter response. Okay, filter response. Let's say if it is kind of taken with respect to unity, like normalized to 1, let's say it's going to have something like this. Right? Let's say this is your corner frequency. Here the corner frequency is 1 by 2 pi r on ch. Right? Now when these two, when this noise goes through this function, so basically what happens is, because it's h of f squared, let's say the actual noise will look something like this. Okay. Now when we are talking about the total integrated noise, we are talking about the region enclosed by this black line. Okay, the area enclosed by this black line. So thermal noise was going up to infinity without any this thing. So if you find out the total integrated noise, it will be infinite, right? Because it's just going on till infinity. Now because of this filter, you basically have only some amount of noise being taken, and the total noise that is being produced by the circuit, the total power of noise, the noise power is basically kT by c. Okay. Now the interesting thing is, if you look at this expression, it is independent of R, right? It is independent of R. Why do you think it is independent of R on? See, the original noise source is 4 kT R on, which is a function of R on, right? And the filter is also a function of R, but the total integrated noise, which is the area enclosed by the black curve, basically that is independent of R. Do you guys have any explanation for that? See, as R-on increases, what happens? This term will increase, right? 4kT R-on, so this will go up. At the same time, what will happen to this FC? FC will move to the left, okay? So both these effects are actually compensating each other, okay? So the total integrated noise basically remains the same. So the total integrated noise depends only on the capacitor, okay? Because depends on the temperature obviously, but it has the capacitor. So now if you want your noise of the sample and hold circuit to be less, what should you do?
Increase the capacitance.
We have to
Load capacitance. Increase the load capacitance.
increase the capacitance, okay? So to improve noise performance, what we need to do is CH has to basically go up, right? So you remember in last class I was telling you that we will be seeing why capacitance, usually CH will be, we will try to increase it as much as possible, and that is basically precisely for this particular reason, okay? All right. So now let us put both noise and nonlinearity together, okay? So now what happens? Let's talk about SNR, right? Signal to noise ratio. So if you assume V in, oops, okay, yeah, let's say V in is given by A cos omega t, right? Now what is the signal power? Let's
A
assume
square.
some A squared. Is it A squared?
Square by 2.
A squared by 2. A squared by 2R actually. But if you normalize, okay, so if you calculate the SNR, right, so A squared by 2 into some load resistance will be here, A squared by 2R. And what is the noise power? KT by
KT
C.
by
Okay.
C.
KT by C. Okay. So A squared by 2. So we assume that there is we just take A squared by 2 as our the signal power. This is just for it is understood when you are doing this. You know that the voltages are across capacitors and there is no real impedance across which these voltages are being taken. So you just assume you just take the voltage squared and you leave out the impedance. So the actual power will come. The notion of power comes only when there is a real impedance, right? So if across C, if there was some resistor RL, then we can define an effective amount of actual power. In the event that there is no resistor, okay, we just assume R to be 1 and we take the ratio of the quantities, because the moment you put the R, it will basically scale depending on the resistance, okay? So the SNR is basically going to be A squared by 2 divided by KT by C, or in other words this is going to be A squared C by 2 KT, right? Now if you look at HD2, there is also another this is signal to noise ratio. There is also what is called as signal to noise plus distortion ratio, okay? So I'm not sure you guys have encountered this term. Have you guys encountered this term? It's
No,
called
sir.
as
No, sir.
SNDR. Yeah. So SNDRs are very commonly used. If you look at any data sheet of an ADC or a DAC, A to D converter, any of the commercially available ADCs or DACs, you will see that there is this, or even these the journal papers, you will see that a term called as SNDR, which is signal to noise plus distortion ratio. And SNDR is defined as this. It is A squared by 2 divided by, it is noise, which is KT by C, plus the power in the 2 omega term plus the power in the 3 omega term, and so on. It is basically signal to noise plus distortion ratio. In other words, this can be written as A squared by 2 plus KT by C plus HD2 squared plus HD3 squared, or basically that divided by 2, okay, and so on. Okay, because we defined HD2 as, oh, I'm sorry. If you use HD2, you'll have to scale the other terms also. So let's just not complicate with that. You can basically, arrive at P of 2 omega from HD. Basically, what is HD2? We said it's the amplitude of 2 omega divided by A, right? And HD3 is nothing but amplitude of 3 omega by A. So if you bring the A down and so on, you can write the same thing. But in other words, we can just stop with SNDR like this. Okay. So if you look at the plots of some of the ADCs, okay, you will, even if you take a product data sheet, or even if you look at any of the ADC papers, you will definitely see a plot which is like this. Okay, they will say this is my this is x-axis is frequency, and this is your output amplitude, and then they'll say this is your fundamental tone, okay, and this is your max amplitude, V max, okay. In the case of an A to D converter, this will correspond to the voltage that will give you the full code, right, all ones. And then what will happen is you will also see some noise like this. Usually these are measured plots. If you are doing an A to D converter, what you do is you give a single tone source of max amplitude, right, send it through an AC, right, you get these bits. These bits you feed it into, you capture these bits using logic analyzers or some FPGAs and so on, and you take these bits and you do FFT. Okay, and when you do FFT, you will see all these things. Okay, so what you will see is that there is a tone which is sticking out of the noise. Okay, and also you will also see some tone which is way down here, and some other tones. Okay, so if this is F0, this will be 2 times F0, 3 times F0, 4 times F0, and so on. So typically you will see only the second and third harmonics maximum, and what they will define as SNDR is basically like how we did. Okay, so let us say this is A1, this is A2, this is A3, A4. Then how you define SNDR is nothing but A1 squared by 2 divided by KT by C plus A squared divided by 2, A2 squared divided by 2, A3 squared divided by 2 plus A4 squared divided by 2, and so on. Okay. So this becomes your signal to noise plus distortion ratio. Okay. There is also one more term which is called as SFDR. Okay, this is nothing but spurious free dynamic range. Okay, you will also see this term in any data sheet, or for that matter any ADC paper. SFDR means spurious free dynamic range. In other words, what it is saying is, all of us realize what is dynamic range, right? What is dynamic range? What do we mean by dynamic range? Let's say in the context of an ADC, typically, dynamic range is defined as DR, defined as the max amplitude minus minimum amplitude. in the case of an ADC, what we are saying is, what is the maximum input signal that the ADC can measure minus what is the tiniest input signal that the ADC can successfully measure, right? In other words, Vmax beyond this, what will happen? It will start clipping. I think, okay, maybe when we look at the quantizer, you will understand it even better. Every ADC will have a maximum amplitude up to which it can measure. What is going to set the minimum amplitude?
Noise.
Noise, correct? So if there is a very small signal whose amplitude is somewhere here below the noise floor, it really cannot successfully measure it. Okay, so that is what is called as the maximum amplitude that the ADC can measure, or in the case of a D2A converter, what is the maximum amplitude that a D2A converter can produce minus the minimum amplitude that it can either measure or produce. Okay. Now, the spurious free dynamic range basically means, right, what is the dynamic range in which there are no spurious terms? Okay. There are no spurious components. What is spurious components? Unwanted components, right? Now here you want only the F0 component because your input consists of only F0. This 2F0, 3F0, 4F0 are all unwanted components which ended up being there because of nonlinearity. Okay. Now this, we said in this discussion, we said the nonlinearity is coming from the R-on. Now in the case where you have an input buffer and an output buffer and so on, like at least the input buffer's nonlinearity will also come into the picture. Okay. So if what this SFDR basically means is, what is the dynamic range where there are no spurious terms? So that is basically given as the maximum amplitude to the maximum amplitude where there is, I mean, what is the spurious free range? This is what is defined as the spurious free dynamic range. In other words, that is the dynamic range in which there are no spurious components or spurious terms. Okay, you can see that the A1 minus A2, that is your spurious free dynamic range where there are no spurious terms. Okay, all right. So now what we will do is we will just come back to our. Let me stay with this slide here. Okay, our V of 2 omega. Our HD2, right? So what happens? How is our HD2 coming here? Let's probably just go to that particular slide, right? So what is the coefficient of Vn squared here?
C omega alpha 2.
C omega
Alpha 2.
alpha 1.
Alpha
Right?
alpha 1. Alpha
Alpha
1.
1.
Yes. Alpha
Right?
1.
Yeah,
Yes.
C omega alpha 1. Okay. Same way Vn squared, what is it going to be? C omega alpha 2. Right? So the coefficient of this, of course, this will have some modifying factor, like you'll have divide by 2 also, because cos squared, when you expand, you will get that divide by 2. Here you will have the 3 by 4 and those things. So whatever those constant terms of, let's just leave them. What you can see here is, as you increase this capacitor, what happens to the strength of these terms?
Increases.
Yeah, it will also increase, right? But if you go to this slide, okay, what happens to SNR? SNR will increase as you increase CH, basically your SNR improves, correct? But if you increase your CH, you will also increase your P of 2 omega, P of 3 omega. This will also get increased. Okay. So there is a kind of a trade-off. There is a balance. You basically will have to do. Another thing that your HD2 is basically going to depend on is the amplitude A. Right? If you have a low, if you decrease your amplitude, what will happen? What was the expression here? C omega times Vn. So if you say Vn is A squared omega thing, the coefficient of 2 omega term will also have a squared, right? So V of 2 omega will be a squared c omega alpha 1, and this will have a cube c omega alpha 2 with some other scaling constants. We'll ignore them for now, correct? Now, if you reduce your amplitude, what will happen? Your HD2 and HD3 will reduce, correct? In other words, typically if you have any nonlinear system, for that matter any amplifier or whatever it is, if you have lower amplitude signals, you will have lesser distortion, right? Higher the amplitude, the more the distortion. That is typical for any amplifier, any nonlinear system, and that is the case here, right? You can see here that the HD2 component has a dependence on a squared, and HD3 has a dependence on a cube, correct? Because we have V in squared and V in cube here, right? So if you drop the amplitude, what will happen? Your HD components will go down, but also what will happen? Your numerator is also going down, okay? So typically that's not the solution. You cannot, you typically want your ADC to have the maximum range as possible, right? You can't tell others, okay, my ADC, I have designed an ADC, but it's not really that good. So you, although my supply voltage is, let's say, 1.2 volt, you can work only up to 0.8 volt. Then people will say, I don't want your ADC, I will go to something else. But this is the way things behave. This is important for us to understand that your distortion tone, that is why this figure that you would see in any of the product papers, product data sheets, or for that matter even research papers, you will see that they will put this figure for the maximum amplitude, because as you increase this tone A1, as you decrease this tone A2, okay, what will happen is, I was just messing up the terms. If you reduce the input amplitude, that is this term A1, if it reduces, what will happen to A2? A2 will go down by A squared, A2 squared, right? And A3 will go down by a cubic factor. So obviously your tones will all start going down. And in fact, your worst case tone will happen for the maximum amplitude. So usually the benchmark is done for the max amplitude. You feed in the input which is having the maximum amplitude. Okay, basically this is nothing but a sinusoid of A1 cos 2 pi f naught t, and then you digitize it, you take the bits, do an FFT on it, and you'll basically see the noise as well as the harmonic components. Okay. And then here you will figure out what is your SNR, what is your SNDR, what is your SFDR. Okay, all these things you will basically figure out. This is how people characterize their ADCs, and this is how you will have to do it in simulation also. Okay, when you are building an ADC in your project, so you first send in or a sample and hold circuit, whatever you are doing, you take it, you put it, take the bits, put it through MATLAB or any other tool, equivalent tool, find out the FFT and look at the spectrum. Okay, is it clear? Any doubts? Any questions?
No, sir.
Okay. So next class, what we will see is, we know that this R-on is a very critical thing, right? Because once you distort the signal here, after this, you cannot improve this. So we need to have a very nice sampling switch. So there's what is called a technique which is called as bootstrapped switches. So we'll look at it in next class. Okay. So if there are no other questions, we'll wind up the class today. Okay. Thanks everyone. Have a nice afternoon.
Thank you, sir.
Thank you. Guys, and one more thing. I just want you to create a group for mixed signal VLSI. Okay. A WhatsApp group, so that will be useful. I think anyway, it's all your classmates only. That will make it helpful easier for me to pass on information or discuss timing. So what happened? Only 5 students have attended today. The other 2 didn't know about the class, or?
So some of them are having internet issues. So
internet issues. Okay. 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 Anyway, I'm uploading all the lectures in the Moodle Play in YouTube and putting the link in the Moodle page. I think it should be fine. Okay, guys. Thanks everyone. Have a nice afternoon.
Thank you, sir.